So why don't we get things started? So welcome to the x86 architecture and its relationship with C workshop. All right, so the first thing that we're going to go over, and I feel this is a very important thing to go over, is the different words that we have for different terms, essentially, and different sizes of data. So, of course, one good way to think of this is with the C data type, right? You have your char, you have your short, you have your int, you have your long, essentially, in C, right? And each of those represents a different width of integer, despite the fact that they all still represent integers, right? So a char is 8 bits, 1 byte. A short is 16 bits, 2 bytes. A normal integer is 32 bits, 3 bytes. 3 bytes, 3 bytes. No. I did that wrong. I'm going to fix this right now. This one is 8. This one is 4. Do not go through this too fast. Tried to do this too fast, and I messed up my byte widths. All right, yes. So an integer is 4 bytes, and a long is 8 bytes. And the names that we actually have for these carry over from the very early days of programming. These are like the official names, and you'll see these come up a lot when talking about assembly. So a char, or just a byte, is quite literally called a byte, and you'll always see the prefix B. A short is called a word. Don't ask me why. And then byte, half of a byte is a nibble, but we rarely deal with actual nibbles as data types, which is 4 bits. But then we have double word, which is 2 words. That's why it's called a double word, and a quad word. Sometimes, and this gets really confusing, a double word is also called a long word, despite the C type being called long. And we're actually probably going to see the suffix on some of the assembly instructions, L, which, don't get confused, L does not mean move long, like long quad word. It means move long as in a double word. And that's going to be, that definitely is one of those trippy things where the C type is not named the same thing as the normal thing that we refer to it in assembly language as. So we are going to move right along here and talk about registers in x86. So this is one of the first things that you need to learn when dealing with an assembly language is the concept, essentially, of registers. So physically, registers are small little locations on the processor for memory to be stored inside. Essentially, we can think of these as the memory locations we can think of them as a set of variables that we're able to operate on with assembly instructions, if you prefer. Now, this is a list of some of the registers in x86 on your processor. However, we really don't care about probably most of these, honestly. All we're going to be using are these few registers right here: EAX, EBX, ECX, EDX. I don't even think we're going to be touching ESI or EDI today. And we are going to be touching ESP, which is the stack pointer, and EBP, which is the base pointer. And let's go back a bit for just a second to talk about really what the use of registers is, because you might be wondering, well, why do we use registers at all? Why don't we just use program memory? Why don't we just use RAM to store all of the stuff? And the reason is because fetching things from RAM is exceedingly slow. So the way that we get around that is the PC has a cache, or the CPU has a cache on it, and depending on what is needed when, it will switch values out into all of the registers, especially if there's a value you're going to be using quite a bit. You want it to be stored in a register. The compiler gets to determine what is and what isn't stored in a register, unless, of course, you're writing the assembly program yourself, in which case you get to decide what's stored in all of the registers. And also, of course, some assembly instructions will not let you access address directly into memory. There's no way to move the value of one memory location to another memory location in x86 without first storing it in a register as an intermediate. So essentially, you can't move one RAM location directly to another RAM location through the processor. First, you have to store it in a register, and then move the register into the new RAM location. It's kind of like when you want to switch two values of the values of two variables. Okay, so let's actually talk about the structure of registers. So registers are 32 bits wide, at least the ones we're going to be working with. We actually are going to be working with the 64-bit wide registers, but for all intents and purposes, what we really care about, especially with the operating system, since it's a 32-bit operating system, we're only going to be working with the 32-bit registers. So here's how this works, essentially. The registers, the entire thing, let's just look at EAX right now. EAX, the entire thing is called EAX. This entire 32-bit register is named EAX. But there's subsections of this which we can refer to by name as well. So we have AX, which is the lower 16 bits of EAX. We have AH, which is this weird middle, the top. This stands for A high, and this stands for A low. So A low is the lowest 8 bits of the EAX register, essentially. But actually, in the big picture, if we back out here, we actually see that there's an even bigger one called RAX, which is a 64-bit version of this. So we can basically access subsections of this depending on the size of our data. And this is very useful because we want to store basically, integers, pointers, and since pointers are the size of whatever system they're on, if we're on a 64-bit system, we're going to need the entire 64 bits of RAX. And especially the register stack, or not the register stack, the stack pointer and the base pointer are quite literally just pointers. So they need the entire full 64 bits, as we can see here, of whatever system they're on. So we are going to be using RSP and RBP instead of ESP and EBP in some of our demos, but in the actual operating system that we're going to be showing off later tomorrow, we are only going to be using ESP and EBP. So essentially, these registers are, again, just to review everything, memory locations on the processor that are able to be accessed extremely quickly, and we're going to be using these as our operands to our assembly instructions. Now, I would like to, perhaps it's a good idea just to show off a little sample assembly program first. I have Hello World written out here. I can make this Hello World quite fast. Can everyone see this? I did share screen, right? Yeah, okay, good. So as we can see here, we are using registers left and right immediately. We have RSP, RBP, EDI. Oh, we are seeing EDI today. I didn't think we were going to get to see EDI today. It's good to see EDI. We have EAX here. So here we're using 32-bit registers. But let's for a second, let's see. I want to move an int to a register just to be fun. If I say return, let's say 10 from this, you'll see that we are putting, this probably doesn't make that much sense since I haven't gone over any of the instructions yet, but as you can see, if you want to interpret this as we are quite literally just shoving 10 into EAX. And I will go over the actual syntax of this a bit more later on in this presentation. Okay, so now that we've covered registers, let's cover sections of an x86 program. And I'm sad to say this is the one area where I do not really have a good demo program to show off it. But the basics of an x86 program, essentially, what you have to know is the fact that x86 is stored when you actually compile it down into machine code. There's different sections of that machine code and the program where things have to be essentially like placed in, right? So we want to split things up into data, essentially, the BSS section, which is uninitialized read-write data. And we also have text, which is the actual machine code instructions that we are going to be executing. Now, I did want to show this off just because I did not mean to do that. There we go. I'm going to show off, not joswald.net. What's the IEEE address that we have? It is, nope, that's the desktop version of that site. I want IEEE, where are we? I know we have, what's our student branch? IEEE UAlbany. I know it comes up in Google now. All right, we go to this. See ya. Excellent. Okay, so this is not x86 assembly, but I feel like this will give everyone a generally good idea of how the different sections work in x86 assembly. So when we compile a program and actually into machine code, so this is an assembly program, not in x86, but in the C language, it basically compiles down into ones and zeros, which we're representing with hex here. But all of these instructions, they do get turned into numbers, right? Like it's all just ones and zeros here. So what happens then when we actually go to run the program, we see that this entire first yellow section here is our instructions. So if I actually start running the program, you can see it's stepping through and executing these instructions. But you see that at the same time that there's all of these zeros here. And these zeros are going to be where we're going to be reading and writing our memory from. So we need separate sections. So down here where we have the stack growing up, and believe me, I'll be talking more about the stack later on, we can see that this is basically, it's all in the same contiguous memory segment, right, that we've loaded the program into. But we might want to initialize like constants outside of the assembly instructions. Say for some reason we wanted to have a constant, we might put something right here and want to reference it somehow later on in the program. And we'll do that with labels, which I'll go over a lot more later on. But essentially, the core thing to take away here is the fact that all of our data, all of the stuff that we push in, we need, it's all in one contiguous memory segment. And when we're writing the program, we want to have a way to tell the assembler when it generates this machine code, hey, I want to put my variables that I've declared somewhere not inside of the actual machine code section. So what we actually end up seeing happen is we have these different sections, and we use BSS for uninitialized read-write data. So what does that mean? That means it's basically an area of memory that we have not zeroed out that we want to be able to read and write from. So this is most of the time where we put uninitialized globals. We'll see uninitialized global variables will be put into the BSS section. And we will see various other things like data here. This is initialized read-write. So this is where like an initialized global would go. For example, if I say int c equals 5 above main, that is an initialized global. So we'll see that actually stored in the data section, while we'll see something that isn't initialized stored in the BSS section. And also, it's very common to see, especially in operating systems, you're going to put your stack in the BSS section. I can actually show that off right now. In the boot, one of the first things I do is I set up the stack in the BSS section by declaring this the BSS section, and then essentially skipping a bunch of bytes and then calling this the top of the stack. So I'm quite literally just declaring my stack for my C program in the BSS section. Okay, so let's actually talk about, so of course there's all of these other sections as well. A lot of this is for debugging and like, you know, some more niche applications. All we really want to care about is BSS, text, and data. And the first thing I'm going to show off actually is the fact that we can see these sections at play almost immediately. So let's call print hello world, printf hello world. Hello world, there we go. And let's filter, I'm going to unfilter directives so we can actually see what's going on. So you're actually going to see that the first thing that happens is, okay, so they're actually not using data. They're using RO data, which for all we have to care, hang on, let me dash G0 to disable debugging labels, and okay, this is much nicer now. So we can see right away what's actually going on here. Ignore this .text up here. I'm not entirely sure why they put that there, but the first thing we see is that we're actually declaring a section here for RO data, which we did see in this as RO data being down here. This is read-only data. So for example, if we have this string in memory, where is it? We have this string hello world in memory. We're not storing that in the program code. We're storing that separately in the special read-only data section. And then this .text right here is basically saying, okay, now we're starting assembly program code, and that's our actual main function. So I'll definitely go more into the actual instructions and labels and everything later on. But for now, I just want to give a brief overview of this different sections of the program. And honestly, I probably should have gone over that after I introduced directives. So let's actually take a look at the structures and things that you'll see inside of an x86 assembly program. So one of the first, these are basically the only things you'll ever see in an x86 assembly program. These are like the only things you can possibly see. So you see, first of all, we have instructions, and instructions take the form of an instruction name followed by some operands. And this is actually what gets converted into machine code and is run on the processor. So some examples of this, we have movil, jump, and then their operands afterwards, with potentially, it can have up to 3 operands. I think actually there's some that have the ability to have more, but most of the time you're going to see 1 or 2 operands, and some instructions have no operands. So an operand, you can think of an instruction if you want as like a function that takes parameters, and these operands are the parameters for the function if you want. But it's probably more helpful to think of instructions as quite literally just being the base unit of execution, even if that's not entirely true. Anyway, next let's talk about directives. So directives are what we're actually sending to the assembler. And the assembler is going to has special internal, code to convert directives into instructions for special things. And a directive begins with a period and then has nothing after it, and potentially can have parameters as well. And these directives tell the assembler what exactly to do in a specific location. And an example of this is what we just saw previously, is actually doing the sectioning. When you do .section.text, you're telling the assembler, hey, this is my text section. And even though this isn't making it into the final machine code, it is making it into the assembly program. And then the linker is going to be dealing with the actual directives as well, I believe. So next up, we also can declare string like this, by the way, as I will show off later on in the next section. And then we have labels. Now, labels represent a named memory location. So this is one of the big hiccups with learning x86, is the fact that people like to think of any name, like variables and everything. People don't really associate these names with memory locations. But in reality, you should associate literally every name with a memory location. And you can do this in C as well, which we will go into more later. As you can see, we have main with a colon after it. And the way you declare a label is with a colon. And fun fact, you can actually declare labels in C as well, and just inline them. I will demonstrate that on the next slide probably. And then finally, you have local labels, which begin with a period and end with a colon. And it's functionally the same thing as a label, except you can have multiple of the same local labels that get associated with a parent label. And we're probably not going to actually go into doing that ourselves, and we're just going to let the compiler figure out whether it's a local label or a global label, even though this isn't technically, no labels are technically global by default. You have to declare them global. Anyway, so let's talk about labels for a second. It's very easy to see what the labels are, right? Because they always start right here on this side. So we have LC0, main, and L2. And the way you can tell it's a label is because it always has a colon. Anything that has a colon after it is a label, especially in this syntax where we are indenting the instructions after the labels. It's much easier to tell what the labels are now. So basically, labels represent locations in memory. And the way that we're going to think about this is the fact that these quite literally compile into numbers that get put in memory. So main is actually just the pointer to the beginning of this instruction in memory. That's all main is. Same with LC0 is the pointer to the location this string begins in memory. And LC2 is the pointer to the start of this instruction. And as you can see down here with the jump call, we're actually going to be able to use these labels as locations that we can jump to, since they're quite literally just pointers into memory. And as you can see here, we're also accessing LC0 directly. We're pushing the memory location of LC0, we're moving that into EDI, and then passing it to printf here. So this is actually very powerful, the fact that we have access to labels, because this is really going to allow us to have not only program control flow, we're going to be able to also use these labels to store variables. So labels have the twofold purpose of being named locations within our program that we can jump to, as well as places that we can store variables and then push, essentially, we can essentially, use those locations of those variables for our calculations if we want, rather than having to use directly storing things using immediates, which I'll go over in the next slide. So before we move on, I think it would be a good idea to actually show off that we can use, okay, let's disable directives temporarily so we can just focus on the nice, simple things here. All right, we're going to delete G0, and now let's actually take a look at what's going on with this program. So that was, I'm pretty sure this is the same program that I'm demonstrating here. No, okay, it's different because I wanted to show off labels, so I was using a while loop for a jump. I was doing while 1 and then doing print hello, print f hello. Okay, so this is not Python. Fixed. Okay, so this is the program that I was showing off in the actual slide. And it's very easy to see where the labels are again, right? They're just these green things here. So what actually is going to happen is when this gets compiled into machine code, which we can actually demonstrate, but it's not going to be very pretty, compiled to binary, we can actually see the ones and zeros, or in this case it's hex, that all of our instructions get compiled down into. Now, what's actually going on here is I really don't want to go into the compiled ones and zeros of the program. But as you can see, when we call jump now, we're jumping to 401126. And 401126, if we actually look at where it is, 401126. So we're actually going back to this location right here in memory. These are quite literally the locations in memory of these instructions. And jump is literally saying, okay, go back to this location right here. And that's our while loop, right? We're going from here to here, and then we're performing our call to printf right here in these instructions. And we're basically just going around and around. But I don't want to get too much ahead of myself on the purpose of the instructions. Let's actually go take a step back for a second and just look at the fact that C actually offers these labels as well. So I'm going to disable compile to binary, and we are going to just see the very nice instructions without their binary representations. So, and this jump L2, now we're just jumping to the label L2. We don't have to worry about the memory address. The assembler handles that for us. So let's actually take a look at writing our own labels in C. So C actually offers you the ability to create labels and go to them. This is kind of like a forbidden C feature. You might know that goto is considered extremely bad practice in C and C++, despite the fact that it exists and it's fast. You can very easily, the reason it's so discouraged is the fact that you can very easily destroy your program by running a goto to a different function and then trying to return. It does not end up well. You completely break the call stack and everything. So let's actually just take a look real quick at writing our own labels in C. So, you can have a while loop and everything. So I'm going to actually write a program, and we're going to compare doing a while loop like this. So this is while true, right? Like this is going to loop forever. I'm going to do printf. So this is going to print out hello forever. Essentially, that's what this program does. Now, let's write the same thing, but instead of with a while, we're going to use a label and a goto. So I'm going to call this guy main2, and instead of using while, we're going to write a label here. We're going to say that this is label, and we are going to, after our printf, we are going to write goto label. And now we can see that these are actually perfectly equivalent. These programs, they both do the exact same thing, except here we're using a label in our C program. Now, I assume everyone understands what's going on here. The goto is literally just saying, jump control of the program back to this label right here, and now execute printf. And essentially, this is a makeshift while loop, because this is going to just go on forever. We're not checking anything. You can literally write any loop like this, for loops and everything. It all works. If you wanted to break control, you would have another label down here, which is, let's call this broke. And then we would say, let's say if A is, you know what? I have an idea. Let's demonstrate the fact that a normal while loop can also be converted to a bunch of labels as well. So what's a good idea for a little simple program here that we can use to demonstrate? I think I'll say int a is greater than b. No, int a equals 1. We'll say b equals 2. Okay, so we'll say while a is less than b. You know what? Let's say it's 10 instead. While a is less than b, we're going to print hello, and then at the end we are going to say a plus plus and increment a by 1. And then what we're going to do is we're going to take this and we are going to convert this into its label program instead. Now, what we can use for this essentially is we're going to start off by having the label at the top that's jumped back to every time. So I'm going to call this L1, as they would in an assembly program. We'll just say, hello, you're L1. And then we're going to check our condition. So now we're going to say, well, if that, then we want to go to the end and skip everything else. So if the condition, if the condition is not met, so if not this, then go to the end. And we're going to have an end label down here that happens after everything. Otherwise, we are going to say, now we're going to do our thing, right? We're going to print f, and we're going to do a plus plus, and then we are going to go back to the top, which is L1. And why isn't it like end? Label at the end of compound statement. Oh, because that is supposed to be in thing. Do they not like the fact that it's down below? What are they mad about? Label at the end of compound statement. They make me very sad. This should work. What's not to work here? Label at the end of compound statement. All right, let's Google it. Label at the end of compound statement is because the default case cannot be empty. What don't they like? Okay, that's Arch Linux. What is a compound statement? The default case cannot be empty. You have to break. But I'm already doing goto. This makes me very sad. What if I indent? I assume they're not going to like that anymore. Then if I didn't indent, see, in assembly, this would work. However, it seems that they don't like this model that I've done very much. So unfortunately, it does not look like I'll be able to show this off. However, this should, in theory, work if you wrote this in assembly language. Let's delete this and just go back and demonstrate what's actually going on in our thing here. So essentially, we can see that the format of the label jump case that we were just taking a look at that failed spectacularly is essentially the same in our assembly program if we look at the control flow. And we'll go more into that after I go over all of the different assembly instructions that we're going to be caring about, essentially. So let's move on real quick. From labels, we're going to jump right into the format of instructions, which you've probably picked up on a bit now since I've been going over a few of these assembly instructions. First, we have the instruction on the left-hand side, and then we have the operands on the right-hand side. An instruction can have as many operands as it needs, and it could also have 0 operands. And we'll see that with instructions like ret later on. So let's jump into the different types of operands. Now, there's quite a few different types of operands that you can pass in, and every single operation, every single instruction has its own set of accepted operands. It's like kind of like function overloading, where you can have different types of parameters passed into a function in some languages. Assembly is a bit like that in the fact that you can pass various different types of these operands in different combinations to a instruction. And the way that we find that out is actually by going to the reference page. So let's take a look at the move instruction. move x86. I believe it's this. So here it will show you quite literally every single possible combination of operands you can pass in. And as you can see, I'm actually going to be ignoring quite a few of the different operands tonight for the basic the basic stuff. x86 assembly is notoriously complicated, especially when it gets into some of the niche cases. So we are definitely not going to be going over all of the different operand types. But for all intents and purposes, we can just focus on registers, memory locations, and immediates for now. And this is primarily what you're going to be using, especially if you're down and dirty in the x86 anyway, right? So the first thing we're going to focus on is registers. So registers, as previously mentioned, are very small memory locations within the processor that are extremely fast to access. And we're going to be using registers a lot. And certain registers, of course, have certain purposes. RBP is the base pointer, RSP is the stack pointer, and then everything else is general purpose. If we want a refresher, I can jump back to this. These are the general purpose registers that we can load with whatever we want, and these are the special ones that we're going to be using to represent the stack and the base pointer. And these are special in the sense that, quite literally, the push and pop instructions for the stack use these internally and set their values regardless of what we do to them. So it's not a good idea to use these to store general data. But all of these, these aren't really used by any instructions, except, well, EAX has certain uses with division especially. Division results get stored by default in EAX, but we'll go into that later. So anyway, let's actually talk about registers as an operand. So registers, when they're being used as an operand, they're always prefixed by a percent sign, at least in the gas syntax. And we're always going to be using, at least for me and for this operating system project that we're working on now, we're always going to be using the gas syntax, which means we're always going to see a percent in front of the register name. So for example, here we can see the instruction, push Q, and then percent RBP. So we are going to be pushing RBP, essentially. And then we have, next up, memory locations as parameters, essentially, or as operands for instructions. So essentially, what we're going to be using memory locations for is storing variables. And very often, you're going to see that variables are stored on the stack. And it's in reference with an offset to basically RSP or RBP. Or just RBP in most cases. So you're going to see here RBP, of course, that is the base of the stack. And here we have an offset of -4, which means we are 4 off of RBP. And then you also see we can offset to a label name as well. So here's LGDT, GDT descriptor, and GDT desc is a label name. And this is actually taken straight out of the operating system code. So parentheses around a label or around a register name or a label name means that we are going to be taking the memory location of whatever is in there, right? So in this case, we are going to be moving 5 into this location in RAM. And in this case, we're going to be, unlike here where we're moving 0 into EAX. I put this here just to contrast, right? So I guess it would probably be better just to go over immediates first as well. So an immediate is a constant value stored within the instruction itself, and it's prefixed with a $sign. So here we're talking like $5. This represents the literal value 5 being put in to the EAX register. This is 0 being put into the EAX register. This is 5 being put into the memory location pointed to by RBP -4. That is the best description that I think I can potentially give of this. It gets very, very convoluted very fast with x86. The best way to think of this is to ignore all of the fancy jargon and everything, and quite literally just think of this as, okay, we're going to be taking this as a memory location in RAM. Just look at, anytime you see parentheses and an offset, or parentheses around anything, think of, okay, we're going to be doing whatever we want to this location in RAM, not what's at RBP. So RBP is the pointer to a location in RAM, and when we put parentheses around it, we're referring to the actual location in RAM, not the value that's stored in RBP. We're viewing this entire thing as a memory location now. So on top of that, we can also see we can prefix label names with a $sign to treat them as if they are memory locations, which I don't really understand why they do that still sometimes. Like, the jump instruction does not make you prefix that. I was looking into this a lot before the workshop, and they do not actually explain why they do this in the gas syntax. I don't think you have to. I think you can in some instances, but we'll see some of that when we actually start going over sample programs. So let's move on. I'm now going to go over all of the simple types of basic instructions. So let's actually take a look at what we have going through here. So the first thing we have is the move instruction. Now, the move instruction is the most straightforward instruction in all of x86 assembly, and it's also the most common instruction in all of x86 assembly. You're going to be seeing this. This is probably like 1 in 2 instructions, if not 2 in 3 instructions, are going to just be moves, setting things equal to each other. So the operation of move is counterintuitive. It sets the second thing equal to the first thing. And this is actually different in different assembly syntaxes. So I'm going to pull this up right now and show you how painful this is. If I have int a equals 2, now we can actually, I forgot the semicolon. Here we go. Now we can actually, now that we understand a bit more about the syntax, we can actually take a look at what's going on here. So keep in mind, move L stands for long word. So that's 32 bits. And that's why we're operating on EAX here, rather than, RAX, because otherwise that would be 64 bits and we'd be doing move Q here. I don't actually think I can type in this, can I? Nope. Okay, so let's actually take a look at what's going on here. So when I say move 2 into A here in the C program, I'm saying, okay, this thing A equals 2. Well, first let's talk about what is A. So if I just say int A, is this going to do anything? No, it's not. Okay, because it doesn't, nothing is being stored in it. So let's put this back. So this is probably the most basic C program. And now I think it's about time to actually start going over what's happening. So for a second, ignore everything that's being set up here by the function call. This deals with the stack. We're going to talk about the stack in depth in a later slide. But for now, I just want to focus on what's actually going on in the program, right? So we're using our move instruction here. We are moving the literal number 2, which is being stored in the instruction. And if we compile this to binary, we can literally see the 2 in the instruction. For, let's see, where is it? Right here. See this 02 in the actual instruction? This is actually being stored with the instruction. This literal number 2 is being stored here and then being pushed into this location in RAM. And now let's take a moment to appreciate what the actual location in RAM is. Did I kill it? Oh no, it's just scrolled up. Okay, so what's actually going on here is -4 RBP. You're probably wondering what -4 RBP is. -4 RBP is quite literally just A. It is A itself, because A needs to be stored somewhere in memory, right? Like, we acknowledge that variables need a location to be stored. Now, where is this A being stored, and how wide is A? First, let's talk about how wide is A. Would anyone like to take a guess at how wide A is, based on the fact that it's an int? How many bytes is it? How many bits is it? I can go back to the previous slide if we need a fresh reminder on how wide this is. But I believe I've gone over quite a bit the length of various things. I'm gonna scoot on back. Would anyone like to tell me how wide A is? If not, I will announce how wide A is. I will give 10 seconds for a response in workshop text, and then we will continue. Yes, A is 4 bytes. And now take a look at this. -4 RBP. Well, RBP is the base pointer on the stack, so we're going 4 bytes down from the base to store this value in this int. So what this is right here, this memory location right here, is a 4 byte wide location. on the stack in memory that we are pushing 2 to. So this quite literally represents our A variable. And then we end the instruction by, this is actually, sometimes it gets this wrong. This instruction doesn't correspond to this. This should be in the gray area. But yes, that's literally what in A equals 2. This is what's going on behind the scenes. We are moving 2 to this memory location on the stack, right? So to continue on with what we're doing here, let's go into what I want. What else did I want to review? Where are we on our slides right now? Okay, let's talk about add. Okay, so let's look at a bit of a more complicated program. We're going to say int b equals, let's say 3, and now we want to make c be 2 plus 3. So now we're going to actually start dealing with some arithmetic operations here, which is very exciting. So, oh no. Oh, okay, it's because I I wanted to do a plus b. Here we go. Okay, so now we're actually going to get this addl instruction here. So keep in mind that the suffix on the operation is talking about how many bits it's working with, or how many bytes it's working with. So move L is moving 32 bits, or 4 bytes, and pop Q is operating on something that is 8 bytes. But for now, we're seeing that everything we're working with is still 32 bits, because these are all ints. But if these were longs, say I had longs here, now you're going to see that this becomes move Q instead of move L, because now all of a sudden we're using a 64-bit wide location instead. So I'm going to switch this back to int, and we're actually going to go over everything that's happening here. So the first thing we're doing is we are storing RBP, or we're storing 2 into RBP. So you know what? It's actually going to be useful if I pull up MS Paint here and actually do a Windows, is it Windows Shift R? Paint. Okay, let's use Paint real quick and just document what's going on our stack. So the first thing we have is we have RBP pointing at this location right here. So this is our RBP. Okay, so now we have RBP minus 4 on the stack in memory. So this is RBP minus 4. And then down here we have RBP minus 8. RBP minus 8. So what's actually going on here is when we say move 2 into minus 4 RBP, we're saying to move 2, and keep in mind that we're writing our locations up. When I say something happened, like when I say that we need to write something in, we're not writing down, we're writing up, and that's why the stack is growing down, because when we write, we don't want to write to this side. RBP is a pointer to a location. So the first thing that happens when we write 2 to minus 4 RBP, we're writing 2 into this chunk of 4 bytes. This is 4 bytes right here. 1, 2, 3, 4. And then this is another 4 bytes. 1, 2, 3, 4. So basically, we've just defined these locations relative to RBP. And now we are going to write 2 to this memory location. And we're going to be writing 3 to this memory location. And this is quite literally A and B. So this is A right here, and this is B. And we are representing A as RBP minus 4 and B as RBP minus 8. And that is what happens when you declare these variables in C. Int is quite literally relative to the base pointer. So next up, what we're actually going to be doing is now they are moving. Now this is funny. We're going to see another bit of magic move here where you would think that this wouldn't be necessary. You would think you could just add the memory locations directly. You can't. This has to be a register. So what they're doing is they are moving now the memory location. So they're moving 2 to this memory location, A. They're moving 3 to B. And now they're moving B into the register EDX. They're moving A into the register EDX. They're moving B into the register EAX. And then they're running add EDX EAX. So what's the result of add? Well, what add actually does is, this is actually wrong. It's not plus equal. Actually, no, it's not plus equals. It's R2 equals R1 plus R2. There you go. Which, actually, in this case, I think it is the same as plus equals. Yes. Yes. Okay, it is plus equals. What am I on about? Okay. So if we take a look now at our thing, what's going on here is we are saying, okay, EAX, which at the moment is quite literally, so this is 3, this is 2, and we're saying, okay, put into EAX the result of 2 plus 3. So now EAX, by the time we get down here, is 5, because we've just performed that addition. And now we are moving EAX into the value of EAX. We're moving it into an offset of 12 from RBP, which in our case is, if we take a look at what our stack looks like right now, we're seeing, okay, so now we're going down another 4. So this is RBP minus 12. And we are storing our result, which is 5, into here. And we are going to then basically do nothing with that result. We could return that. So if I say return, actually this isn't going to change anything. It's just going to remove the final instruction. This will be funny to see. Yeah, so basically what's going on here with the return C is now we're moving RBP into, we're moving the result C, which is minus 12 RBP, into EAX. And EAX is always going to be our return value from a function. In the event that we're not returning a long, in which case it's going to be RAX is going to be our return value. Our EAX is going to be our return value if it's a int. Otherwise, if it's a long, we're going to be returning RAX instead, which is very interesting to see. And effectively, if you try and return something larger, I believe it then pushes things onto the stack and then tries to push them off. But this is how most returns happen, especially since you're doing pointers. And that's why it's always preferable to return a pointer to something than it is to copy the entire massive structure back into memory. And I could go on and on about how you would actually optimize for this, and it's a very interesting topic, but we are not going to be going into structures. We're just going to be focusing on basic x86 assembly. So now we've gone over these basic programs. Does anyone have any questions about the simple arithmetic program, besides the push Q and move Q at the start and the pop Q and ret at the end? Anyone has any questions about the most basic programs that we've gone over so far? Speak up now, and I will go into how the stack works probably right after this, because I feel like the stack is absolutely necessary to talk about now that we're really getting down and dirty with our assembly language. If you have any questions, you can ask them in workshop text, and I will jump right on in. I love the stack too. The stack is a lot of fun. And that's why I think we're going to start talking about the stack literally right now. So let's take a moment to talk about what the stack actually is. And to demonstrate what the stack actually is, I think there's no better program I can use to show off than my assembly program right here. So let's write a little meme program that does a loop and jumps back to, let's fill the stack up with something. Let's say, let's push, oh god, did I forget the syntax? I think I forgot the syntax. You can only push registers onto the stack. Right, okay. So if how would I jump backwards? I believe it's just, it's literally just relative, I think. It's not, it's an absolute jump. So what I can do is I can say move 1, no, yeah, okay. Move, how's the move work? Yeah, okay, so it's the immediate, so it's move 0 into register 1, and then we are going to, this is not x86, just a reminder, this is a much simpler assembly language than x86, but you can see that it's still generally the same idea, right? We have our moves, we have our jumps, we have our, adds and everything, and our pushes. So I'm going to be using the push instruction to push something onto the stack, and hopefully this will be adequate to show off. All right, so I'm going to call jump 0, which is going to jump to, you know what, no, I'll call jump 1. Let's try this. Yes, this is CSI 404's assembly language. At least it was last semester. Not last semester, the semester before last semester. This is actually done in WebAssembly, which is tied into. I literally compiled this from my C code for my 404 class. So if we actually look at the sources, you can see that this cia.js thing here is actually a JavaScript compiled WebAssembly file. And this, where's the actual, I don't see the actual WASM here, but there is a WASM file. This thing right here. This is the WASM compiled C code from my assembler that I am now running online using EMC scripting. But yes, this is essentially, let's actually, okay, so this is never going to halt. And I'm going to run this, and this is going to be lots of fun. So why don't we move, what's a fun number? Fun number under 255. I would say 39. Yeah, okay, sure. 39 is a cool number. Let us assemble, and we are now going to run the virtual machine. So this is our program right here in yellow. And the same thing would be true if this was x86. We would have our little text section right here, and we would have all of this free memory here. Now, there is a base stack number, but what we're going to do here now, we are quite literally, if we take a look at what's going on here, we're saying, okay, move 39 to R1, this register 1. Now, push register 1 onto the stack. And now we're saying jump 1. And in this case, 1 is relative to the entire program. So you can think of 1 as a label right here. This would basically be 1 right here. But we're jumping to this instruction right here, push R1. So essentially, we're just going to keep pushing R1 until we get a stack overflow. So I don't know how many of you have ever actually seen a real stack overflow, but normally a stack overflow is caused when the stack hits into memory that it should not be hitting into. So eventually, if this stack keeps growing, it'll grow all the way up to the top and start rewriting our program code. And then that's very dangerous because now you have arbitrary code execution. So there's a lot of ways that you can protect against this on x86, such as segmentation. This basically the situation that if this hits into the this stuff, it's game over. But this would not be a real issue on a real processor because they have so many security features to prevent things like this that it's not even funny. So as you can see what's going on here, you see 27. It's not 39 because this is 39 in hexadecimal. But essentially what's going on is we're pushing an int. So every 4 bytes right here, every time we run push, it's going to put whatever is in R1 onto the stack. And in this case, R1 has 39, and you can see that right here in R1, the register itself, right? It has 27 in it, and it's going to be pushing that onto the stack every time it makes that call. So it jumps, and then it pushes. It jumps, it pushes, it jumps, it pushes. So this is the stack. It's basically something that grows up from a location, it grows upwards, or it grows downwards, not upwards. In this case, it looks like it's upwards, but these are actually lower memory addresses. So it's actually growing backwards. Right? It's not growing forwards, otherwise it would be growing down this way, but it's growing down in terms of memory locations. So, and nothing better demonstrates that than MS Paint, where these are actually lower memory locations. This is towards 0, and this is just getting bigger and bigger. But we're growing the stack every time we add a new thing on it. We're growing the stack down. And the way that the stack actually works, and this is very important, is the fact that when we call a function, let's say we're calling a function, what's actually going to happen is we are going to save all of our parameters at these plus locations and all of our local variables at these minus locations. And also we're going to be storing the return address at EBP plus 8, which is also very interesting. But we're not even going to pay attention to the parameters or anything. We're just going to be talking about our local variables, and we are going to essentially discuss how assembly sets up the stack every time you call a new function. So let's go back to our Godbolt and actually start talking about what's going on here and the actual structure of what's going on when you call main. So when we call main, the first thing that we see happens is we push RBP onto the stack. Now you're probably wondering, why are we pushing RBP onto the stack as the first thing that we do when we call a new function? Well, the reason is because this is the RBP of the previous function, the base pointer to the previous function. So say we're calling main from something else. Say we have, and we are calling main from something else. It's actually called underscore start. So underscore start has its own variables and everything. And it has all of these local variables defined. And this is RBP relative to underscore start. So it has its own RBP. And it has its own local variables defined at RBP -4 and everything. So it has all of its local variables, right? But we don't want its local variables. So when we call a new function, say we run, and we're calling main in here, we want to preserve all of our local variables. So instead, what we're going to be doing is we're going to be jumping up to the end of the function at something called RSP. Now, I haven't gone over RSP yet, but if we take a look at the diagram, it should be made abundantly clear what exactly RSP is. RSP, or in this case, it's going to be ESP because it's 32 bits instead of 64 bits. ESP is the top of the stack. It's the last thing on the stack that's free. So if we actually take a look down at this, ESP is always going to be this value right here. It's the pointer to the final location. It's actually, in our case, it's going to be the first free value after the stack, right? So when we're doing our step and we're pushing new things on, we're incrementing the stack pointer. And one of these registers actually is the stack pointer. Which one is the stack pointer? 3 is this one down here, R15. This register right here, this is actually our stack pointer. This always points to the top of the stack. But we don't always want this top of the stack, especially when we're calling functions. And this language isn't versatile to call functions. But languages that are, we want a way to store our local variables. And the way that we store those local variables is using the base pointer, which points to the location, the base of our function's local variables, essentially. So let's actually take a look at what's going on when we call RSP, or when we call a function. So let me go back to our code right here. And just to make things even easier, we're going to forget about everything else, and we're going to go with the world's most basic program, setting an integer equal to 2. Right? So the first thing that happens is when we call main, we now want our own RBP. So we want new space that hasn't been used. We don't want to rewrite. We don't want to overwrite starts variables. We want our own space for variables. So where better to store the variables than in the free space at the top of the stack right here. So we're going to push the stack down and move our base pointer to the location of the stack pointer. So let's go take a look at what they are doing, and you're going to actually see that's basically exactly what they do. But the first thing they do is they store the base pointer so they can get it back later. Because keep in mind, this is overwriting RBP, but we don't want to forget RBP because eventually we're going to have to go back to that function. And when we go back to that function, we don't want to just return control, which is what ret is doing. We also want to have access to the right locations for all of our local variables in that function, which is why we then have to pop the base register or the base pointer back. So now wherever we're going back to has access to all of its local variables. So let's go through this step by step. So the first thing that's going to happen, I'm going to create a little stack for ourselves. So we have some function that has its own RBP, and I'm going to call that start RBP or SRBP. SRBP. So this is the current value of RBP. It's pointing to this location in memory right here, and then all of our local variables for our start function are stored in here, etc., etc., etc. And then finally, at the end, SRBP minus, let's say we're storing 2 things in our start function. So this is going to be -8 if we're talking about ints, if both of these are ints. These are just local variables within our start function. And now we have all of this empty memory down here, right? So at the moment, we have RBP right here. This is our RBP. And this is the bottom of our stack. This is RSP. And this has been set up in advance because the operating system itself has also called into this, right? So now we actually want to figure out what's happening with our assembly instructions when we call this new function. So somewhere within the program code, within the assembly code, they've ran the call instruction, which calls into a function. And what happens when you call into a function, it actually pushes the return address onto the stack as well. And we actually see that here, that we're pushing our parameters onto the stack, and then we're pushing our return address onto the stack. But we're not even gonna care about this. We're just gonna completely ignore this for now because we don't want to get things too complicated. Call automatically pushes this return address onto the stack, and you have to manually push your parameters onto the stack beforehand, right? So let's go into actually what's going on here. I'm going to go back to our program, and we are actually going to simulate what's going on here. So the first thing that happens is we're going to push RBP onto the stack. So the first thing that goes down is, where's RBP at? So RBP, this value here, let's say we need a memory address. Let's call this, you know what? I want to just call this let's call this 100. Sure. So this is 100, and that means this is so this is 92. Can anyone do, no, not 92, it's 96. Can anyone do math extremely fast? This is 92. This is 90. No, 88. Yes? No? I think it's 88. And then 84. And then 80. Looks good to me. Okay, so now we have memory locations for all of our things, right? So essentially, the first thing we're doing is we're pushing RBP onto the stack. So what's actually going on here is we are quite literally storing RBP onto the stack at RSP. So now RSP moves down as we store this in. So now RSP, we take this guy, he goes down here, and we get the value of RBP, which is 100, and that's getting pushed onto the stack. So now this is 100. But now what's going on is we're moving RSP to RBP. So now we're moving RSP into RBP. So now what RBP is actually pointing to is the same as RSP. But what's actually going on here now is I'm actually surprised that they're not incrementing RSP like they normally do. Why is that not happening? They should be incrementing it. Let's see. Maybe if I declare some more things, it will increment it. Let's see. We'll do 3. They want to increment for me? I'd like to see some incrementation. Maybe they don't increment unless I call printf. So what if I do print hello? Sure. Every time I print something, I always, for some reason, seem to have them subtract from it. So let's see if that works. Oh, look at that. Beautiful. I'm pretty sure the reason that they're not doing the subtraction is because they don't have to worry about RSP being manipulated unless you're calling into a new function from your function. So let's take a look at this now, because we want to assume that this is going to happen no matter what. So now what they're doing is they're subtracting 16 from RSP. Now, you're probably thinking, why are they subtracting 16 from RSP? This seems completely arbitrary. Well, this is where the compiler comes in. This is where the compiler is doing all the work for us. The compiler sees, okay, you have this integer right here. Great. Okay, so you're storing this integer. This is 4 bytes. This is 4 bytes. Excellent, excellent. What else do they need? Do they think I'm storing? I have absolutely no idea. But they're also storing, oh, you know what? I think they're storing on our, oh God, are they storing the pointer to the string in line here? They very well may be. We are going to ignore that. I wish they would just, oh wait, you know what I can do to fix this entire thing? I can create an extern function that just does nothing. I can do void v nothing, and then I declare that, I'm going to just declare this extern void v, and then I can just call v here, and then I'll trick it into forcing. Okay, so here we go. Oh, it's still doing 16 even though we're not storing anything. Well, that's odd. I'm trying to figure out why it's storing 16. We don't need 16 because we're not. What's it putting at the end? Anyway, all you need to know is what's going on is the fact that now they're saying, okay, when we move RSP into RBP, we're taking this guy down 16 bytes. So in this case, 88, we're going all the way down. It's because you would think it would be 8, right? Because this guy's an int, this guy's an int. That's all the local variables we have. I assume actually it's probably no, because it couldn't be pushing. I'm very confused as to why it's subtracting 16 instead of like 8, but I'll take it. Anyway, so yes, RSP now gets moved all the way down here, and now RBP is still at this location right here. Now what's going on is now we're actually moving 2 into -4 RBP. This is the new location. So 2 gets put into right here, and then 3 gets put into -8 RBP. This is RBP, -8 RBP, 88 minus 8 is 80. So 3 gets put in right here. And now we call this magical V thing right here. And V doesn't actually do anything, so it doesn't actually matter. And then finally, we're calling, okay, I see what's going on here. We're going to get rid of that. Anyway, so what's going on now is we have to pop RBP back, and then we need to return. So what happens when we actually pop RBP back? So we're calling popq RBP. So what popq RBP does, popq takes the value on the top of the stack. Oh, and you know what? We're not actually. Oh, I see what's going on. That's why they're keeping it here. Okay, this is kind of annoying. I see exactly what's going on here. So they're keeping our SP right here, right? Because they know that we're not calling into anything else. So now what happens when you call popq, it's taking the value at RSP, which is 100, right? So it's taking 100 and putting it back into RBP. So once RBP has 100 stored in it, that means RBP is now pointing right here. And also it de-increments, when you call pop, it de-increments RSP by 1. So now we are back. Oh no, because 100 is up here. We're not moving it up. So this guy gets moved back up here, and RSP is now pointing right here. And we are back in our original function scope and now have access to 3 and 2 before we had called those functions. And this is the stack. This is the hell that is the stack. The stack can get very complicated very fast. And yes, it's the stack is suffering. Does everyone kind of understand how the stack works? Is that a good explanation? I don't think that was a very good explanation of how the stack works. I think if you really want to know how the stack works, we can watch some videos, or you can look up some videos on your own time. Unless everyone here wants a better understanding of the stack. The stack is suffering, as those of you who have experienced it know well. So that's what push Q and pop Q does. Now we have to talk about some of the other fun functions, right? We're talking right now. Okay, so we have to talk about jump, call, and return. And we're also going to talk about compare, but compare is basically how you get your if statements compiled over. So let's go back and take a look at this. So let's get a call going. So I'm going to create a new function. I'm going to call this function int f, and we're going to call let's do an add function. So this is int a, this is int b, and we are going to just return a plus b, and now we're going to return from main the result of add a comma b. So we're returning, well, no, let's do 2 plus 3. So this should in the end return 5, and if I enable output, run the compiled output, yes, give me that output. Program return 5, right? This makes sense, right? We're calling add to do 2 plus 3 essentially. So let's actually take a look at what's going on in our assembly program here when we call a function. And this would have probably been a better example than that stupid start thing, especially if I had done int a equals 2 and b equals 3, and then I just done a and b here. This actually gives us some stuff on the stack that we can look at, which is fun. And as you can see, we're still subtracting 16 from our stack, which we don't actually need to do. I'm not entirely sure why they're doing that. So we're also going to get to see here how parameters are moved around in x86. And there's actually a lot of controversy because parameters can be moved around depending on how the compiler feels, which makes it very hard to call functions with parameters unless you know exactly how the compiler is going to behave. So let's take a look at this program and see what's going on. So the first thing we do, of course, is we set up the stack for our new function, as we just previously went over. And now let's actually take a look at what's going on. So, of course, we're putting 2 into A. We're putting 3 into B, which is at this memory location. Now, we're moving... Oh, God, look at this horrendous call structure right here. It's literally just copy and pasting. If I enable optimizations, this entire program goes away and just returns 5 and does this computation automatically. It quite literally knows, okay, you're calling this function. We're just going to run this function for you at compile time, figure out that it's 5, and just return the fact that it's 5. So we don't, but I'm literally forcing no optimizations just so we can see the actual output of what happens when there isn't optimization. So as you can see, what's going on here is the first thing that happens is, okay, we're moving A into EDX, we're moving B into EAX, and keep in mind these are the values of it. So we're moving 2 into EDX, we're moving 3 into EAX, and then we're moving EDX into ESI, and then we're moving 3 into EDI. Now you're probably wondering, well, what's ESI and EDI? So if we actually go back to the registers and take a look, you see ESI and EDI here. So originally these registers had a very different purpose, but now what these registers are really used for is passing parameters through to other functions. So when we take a look at what they're doing here, they're moving it to ESI and EDI, and then it's just keeping track of the fact that they're coming out on the other side right here. And as you see, there's a lot of unnecessary moves. This entire thing could be optimized by just saying move L2 to ESI. Instead of moving it to the memory location first, we could quite literally just move 2 into ESI. We could move 3 into EDI, call add, and the program would be done. Literally, all of this is completely unnecessary. We could get away with so many less instructions, but this is what happens when you keep optimization off. It, for some reason, behind the scenes, thinks that it's necessary to do all of these moves. And you see the exact same thing up here in the actual function. So what's actually going on here in the function is it's setting it up, right? So this is our typical setup lines. Now we're setting up our own local variables. And the parameters are actually being stored not as... they're actually being moved to the stack. So now we're moving the parameter out of EDI, which in this case we moved 2 into EDI, right? If we follow this chain all the way back up, 2 into -4, -4 into... Oh, they moved... they actually switched it around here too. So it's not even straightforward. Okay, so I'm actually not entirely sure whether 2 or 3 is in here. But then we're moving 2 and 3 respectively into -4 RBP and -8 RBP here. So these are our own parameters now in our new function that we've moved it into. And now we're moving those into EDX and EAX. And then we're calling add on EDX and EAX. And then keep in mind that when you call add, the final parameter is what gets incremented. And it's basically just doing EAX equals EDX plus EAX. And then now we have the result of EAX. And now we're going to pop the register base pointer back so we have access to our original scope. And now we're going to call ret. And what ret is actually doing is returning to this memory location right here. What call is doing, call is actually pushing the memory location right after itself onto the stack. And when it pushes the memory location after itself right onto the stack, what it's able to do then is have ret pop that location back off and then go to that memory location. So despite the fact that there's no labels here, it's able to go right to those memory locations. So when we call ret, it's jumping to this instruction right here, right after the call instruction. So if we actually take a look at what's going on here, and we're going to ignore leave because I should just be putting a... Oh, no, I did put a return here. Okay, so basically what it's realizing is the fact that your return value is always going to be stored in EAX. This int that's coming back is in EAX, right? So then it's realizing, okay, so the return value is in EAX, and now, wait a second, we're returning EAX, right? So EAX already has the value we want, and now we're returning that value. So it realizes now, oh, EAX already has it from up here. So we don't even have to do anything after this. We can just, I actually don't know what the leave instruction does. To be completely honest, this is, if I switch over to Intel and then highlight, it will tell me. What does the leave instruction do? Tell me. Releases the stacked frame set up by an earlier instruction. The leave instruction copies the frame pointer in EBP register into the stack pointer, which releases the stack space allocated from the frame. The old frame pointer, yada, 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 pushed from the stack. Okay, I'm not entirely sure why we need this in some instances and not in others. Clearly, we don't set up anything magical. Maybe it's moving the RSP back in the case that you're doing a sub here. I'm not entirely sure. Let me go back to our nice syntax. Well, people like to say that Intel syntax is nicer. I disagree. I think that this the gas syntax is nicer because we actually have prefixes telling us what every opcode is, or operand is, my bad. Okay, so you know what? For a second here, if we remove that and just have the call happen. I think we're going to see, and it still calls leave for some reason. Great. If I just return 0. How do you like that? It's actually, does it fix it? Nope, they still leave. Okay. I probably am never going to understand why there's this leave here. We'll definitely figure that out at some point in the future. Anyway, let's actually go through, so this has been the call and the return instructions. Now, the final thing I want to go over is the jump instruction, which jumps to a label. And this is how you implement all of your loops in C. Let's take a look at jump. So we are going to have a while loop that loops forever. So while 1, and we're going to print hello. Print hello. And this may or may not crash the this thing over here. Okay, it doesn't crash it. It is an infinite loop. Are they going to tell me I'm not allowed to do infinite loops? Probably. Anyway, let's take a look at what we're doing here. So, oh, it's because I didn't say printf. Okay. Okay, yeah, so they truncated it. They only, and they error coded me because it's an infinite loop, and they don't want you running infinite loops on their server. Anyway, let's go through what's actually going on in this program. So the first thing, of course, as always, we set up our stack, right? And now we see that we're actually declaring this label L2. They're declaring a local label here, L2. And the reason they're declaring this is because we need something to jump back to after we finish, because we want to do this statement forever and ever. So we need something somewhere in memory. We need a little location to reference that we can go back to. So let's actually take a look at what's going on. So the first thing that's happening is we are moving this label, LC0. So LC0 is the memory location pointing to the start of this string, which is this H right here. So we are moving this pointer to this string into EDI, and as you may remember from last time, what is EDI? Well, it's a parameter. So this is our parameter to printf. We're passing the pointer to this string to printf essentially. And then what are we doing here? We're moving 0 into EAX. I have a feeling this is for the return of the thing, but this could also be passing a parameter. I'm not entirely sure. Let me try doing return 0 and seeing if that alters it. Return 0. Why do we need to call this right here? This does not make much sense to me. It doesn't seem like it's doing anything. Move 0 into EAX, but we're not using EAX. Maybe printf. Printf probably is working some magic behind the scenes. Especially, printf is a very weird function, right? Because printf is a Vardic function in C, which there's not many. They basically invented Vardic functions just for printf because it can take a variable number of parameters. So something tells me that EAX right there is actually the number of Vardic parameters. Let's take a look and see if we vary this, if my hypothesis on that is right. So if I do hello %d and then do 1, am I right? I'm not right. Now they're moving 1 into ESI. Well, that's very interesting. I still can't figure out why we're moving 0 into EAX. That's very interesting. If anyone figures that out, please let me know, because that seems like a completely unnecessary instruction to throw in there. Okay, so then they're calling printf, and printf does its thing with the parameters we passed it, right? And then finally, we're calling JMP. And JMP, if you can't tell, stands for jump. And in this case, we're jumping to a label. And in our case, this label is L2. So then it's going to just jump back here and execute this sequence all over again, resulting in an infinite loop that prints out hello forever, essentially. Back and forth forever. And this is essentially all the instructions that we need to think about right now. But just for the sake of the fact that we're still under time, I'm going to be able to go over a few more fun instructions. So let's take a look at the compare instruction real quick, because the compare instruction is very fun. So if we take a look at, let me, basically the question becomes, well, what happens with if statements in assembly, right? We want to have conditional code execution. So conditional code execution, you're going to see, is really handled primarily through labels. So if I have, let's say, if one do, I don't know, what do we want to do? We want to print, let's print f1. And then otherwise, we'll have an else. And then we will print f2. And let's see if we actually, okay, so here we see that the compiler is smart enough to realize that this one is always executed no matter what, and doesn't even include the case for the second one. You can see they're not even bothering to store the 2 in memory. They're quite literally just saying, oh, okay, well, you're saying 1 here. So what we have to do is make sure that it's not able to basically pre-compile this. And the way that we're going to do that is we're going to say a equals 1, b equals 2, and we are going to check if a is less than b. And now we get both cases. So let's actually take a look at what's going on and how they square this up with all of the labels. So we are actually going to see some interesting instructions like JGE and cmpl, which should be the 2 new ones that you're looking at, saying, I have no idea what cmpl and JGE mean. So if we actually go through, let's go through the program. So the first thing we do, of course, we're setting up our stack, as always. We're setting up the stack frame, as always. Then we're moving 1 into here. We're moving 2 into this memory location. So this is A, and this is B. And now what we're doing is we are actually, oh boy, this is interesting. So we're running we're moving A into EAX, and then we're running cmpl. And now what cmpl does is it stands for compare. CMP is compare long. And if we actually switch over to Intel syntax, I can get highlighting on CMP, and we can actually read the Intel docs description on what it does. So essentially, it compares the first source operand with the second source operands and sets the status flags in the E flags register according to the results. And okay, so we haven't even gone over, I wasn't even planning on going over the status flags register, but essentially the status flags register stores different flags. So if I take a look at x86 flags, this is actually pretty important. The flags register in x86 contains 32 bits of information. Actually, there's a 64-bit version now, basically about the results of certain operations. So certain operations will trip flags in here based on what's going on. So for example, the thing that we care about right now is we're going to be checking, I believe, the 0 flag. And they set the 0 flag in the event that I believe the result of an operation is 0. And I believe that compare will set the 0 flag if the 2 things are equal. And then what we're going to have happen is do JGE check whether or not that's true. Okay, so it checks the state of 1 or more of the flags in the status register. If the flags are in the specified state, performs a jump to the target state. Yeah, okay. So I believe what's going on here is compare here, and let me switch back to Intel syntax. Compare is basically saying, okay, is EAX equal to B? And you're probably wondering, well, why aren't they just comparing the memory locations? Again, you can't. If we go actually look at the CMP instruction, docs x86, you're going to see that there's no such thing as CMP x86. Can I get the docs? I want the CX8 website. Is this going to give me a good thing? All right, this is fine. This is basically the same thing. As you can see here, there's no way for you to compare two memory locations. And these are our memory locations. And the reason that they're using EAX is because it stores in a smaller opcode, and they can optimize the size of it, which, oh my god, we can't go into because I would be in so much pain and we'd be sitting here for another 2 hours if we went into actually how they compile x86 assembly into its various opcodes and everything. But essentially what we're doing here is there's no possible way for us to compare two memory addresses directly. You see, a memory address is called an M8 or an M16 or an M32 or an M64. M64 is a 64-bit memory address, like 4 bytes wide, essentially, right? So you are not allowed to directly compare two memory addresses. First, you have to move one into a register. Otherwise, well, there is no otherwise. You quite literally just aren't allowed to. All right, so let's go back and take a look at what we're doing here. So we're comparing EAX to the B memory location, and then we're running JGE, which does jump if the 0 flag is set. So this cmpl is setting our 0 flag, and then we are running JGE to L2, essentially, right? So L2 being, where is L2? Down here. So they are jumping to L2 if this condition is met. So if, it's JGE's jump greater than or equal to. Okay, so it's setting the flags in the flags register. I see what's going on here. Okay, so what are they doing? It's probably the sign flag, and they're probably setting something else as well. I'm pretty sure they're probably setting the 0 flag and the sign flag in some combination to check if it's greater than. And with that, they're able to actually figure out, okay, is the result of this comparison, would that mean that this is greater than or equal to if A is really less than B? And the reason they do jump greater than or equal to is because here we see, okay, so here you see that this is less than. So you're probably wondering, why are they doing jump greater than or equal to? Well, that's because we want to not jump in the case that it's less than. Otherwise, we do want to execute the code right after it. So it actually has to be the inverse logical condition of what we have. So instead of A less than B, we're doing greater than or equal, and because we're saying, okay, if A is greater than B, then go to our else condition, rather than saying, okay, and then if it's less than, we're just going right through what's right after it, right? So we're saying, okay, once we do the comparison, if the comparison is true, then we're jumping down here, and we're running our else condition, which is printing out 2. LC1 is where they're storing 2 at. And otherwise, we're going through our red code, and then once we're done with our red code, we're skipping over the else statement with this, the else statement with this jump L3, and jump L3 is moving down here, basically right after the statement, right? And then we're just leaving the function. So that's basically how we deal with conditionals in x86. A lot of languages have this a bit nicer. For those of you who do MIPS, it's much prettier, I would say. Carter asks, is compare used for conditional jump to by setting the result flag as the condition? So basically, this is the conditional jump. Compare is used. JGE is the conditional jump. Except it's 2 instructions. There is no single conditional jump. This is the conditional jump, is the combination of these 2 instructions. CMP is setting flags in the flags register. And then the jump is looking at those flags to determine if the case has been met for a jump. And unfortunately, I cannot tell you off the top of my head which flags are being set by CMP. If we actually take a look at CMP, we can probably figure out what it's actually doing. So all it's telling us is it's modifying the flag structure. I want to actually know how it's modifying the flag structure. Yeah. So the CF, the OF, the SF, the ZF, the AF, and PF flags are set according to the result of the compare. But they're not telling me the exact flags that are being set, and that kind of annoys me, because I really want to know. All they're saying is, oh yeah, once you set the flags, now we're able to tell using JGE whether those flags have been set in such a way that the result of that comparison means that we're allowed to jump. But yes, this is the conditional jump. There is no such. JGE is essentially the conditional jump, except you're basing your condition on the state of the flags after a compare. And the reason that they split this up, I believe, is because there are certain ways that you can do this where you can do just a conditional jump without having to run the compare first, because you have already, either precompiled the result of that operation, or you're doing a second jump or something, and the flags are already in the right state, I imagine, and you don't want to edit it. I feel like that would be a good implementation for. I'm trying to think. Maybe that's how you could implement a extra fast switch statement. But we're probably not gonna look at switch statements, because switch statements, they actually compile. I would show off switch statements, but we'd probably be here for another 20 minutes. But basically, we've gone over now the most basic of these. Did I X out of it? No. Okay, good. So we've gone over all of the instructions that I wanted to go over. So hopefully you have a fuller appreciation for the x86 language. Now, how many instructions the x86 language actually has borders on, I think, if I Google this, it's not even going to be a concise answer, because different things add different instructions. But let's see. How many instructions in the x86 language? And, 1,503. And we've gone over about, 10, if even. So, unlike MIPS, which has 30 instructions, or a language like ARM, which also only has a few instructions, how many instructions does ARM have? 16. And as you can see, MIPS probably has, let's see. Are they not going to tell me how many MIPS instructions there are? I believe there's not more than 32, right? Am I crazy? There might be more. Anyway, as you can probably tell, so 16 for ARM, which is, of course, what you have in phones and everything. And then x86 has over 1,000. So it's kind of crazy to just think about the fact that we've only gone over a few of these, but there's literally millions of these. And I think we can find the x86 instruction set list, and this is where things get very very. So we can just go down and look at all the different instructions that they have in the x86 language, and every single one of these is an instruction that does some operation. And the reason there's so many is because they can make things insanely fast when you have this many hardware supported operations, essentially. So if we actually, yes, here's the really long one that has all of them. I'm gonna post this in, and as you can see, there's some insane ones that are insanely long. VP broadcast TB. Yes, that's that's not what you want to see in your assembly program. And honestly, you'll probably never encounter most of these. Oh, look, these are exclusive instructions to the Xeon Phi processor. And of course, that's because most of these instructions are hardware supported, linear algebra operations, which makes it insanely fast. So you're able to, the whole big thing is, you want to get as much, linear algebra done for your data mining and your machine learning and everything. And if you don't want to run it on GPUs, you gotta run it on your CPU. And these vector operations, everything prefixed with V stands for vector. So it's all of these super fast data processing instructions that are hardware supported, and then they write special C libraries for these just so you can use these instructions. Anyway, back to x86 and its relationship with C. We've gone over just a few of the instructions, as you're probably aware. And honestly, we've seen most of the normal stuff that people use. Things get a bit more weird when you start doing floating point operations, since you're using the XXM registers. or maybe it's XMM registers. Or is it XXM? Well, now I want to look. Let's go take a look at our register page. It is XMM. Okay. Yes. So these are like big special registers for floating point operations that you'll actually, I kind of want to show it off because it's kind of cool. If we actually try adding 2 floating point numbers. So now I'm going to declare double. I'm going to say double A equals 0.01. And they don't like that because I don't have a guy on the end. And now you're seeing we're actually storing things in these new XMM registers. And we're essentially operating on that. So if I actually do floating point operations, you're going to see that they have special floating point operations for different things. So if I do A plus B, let's say double C equals A plus B, you're going to see that they have special floating point add instructions and everything. Add SD. And instead of move, we're doing mov SD, which is the special variant of move for these XXM registers that are of wider width and have these, they basically, these are the floating point variants. And if we go over to Intel, we can see them without the, they literally still have the SD on the end, even in Intel, yes. So essentially, even just switching over to floating point, which has a different format, we're using completely different instructions for that because there's a faster hardware supported way of doing it. And that's really the gist of x86 assembly, right? Is the fact that there's always a faster way to do things on hardware, and every single instruction corresponds to something that's actually being done physically on the processor, which is why we have 1,503 instructions. It's because it's so much faster to do things on the hardware than it is in the software, even if you're working at the assembly level, right? So we are now going to continue and finish this up with this program here, which I wanted to show off as the first assembly program. Little did I know that this would be the last program I show off. And this is just a simple program to add 42 to a number coming in, I believe. So and this is also, it's translating it to C right here. It's actually showing off the operation. So what's actually going on here is this is this frame setup, these first 2 instructions. We're setting up the stack frame. We're pushing RBP onto the stack, and then we're moving RSP into RBP, or the value of RSP, we're setting RBP to. And then we're going to set, okay, so EDI is our parameter coming in, and we are going to set that to whatever -8 is here. So this is a variable. We can really basically tell what's going on in the C program above it just by thinking of all of the memory locations as local variables when you're offsetting to RBP like this. So this is a memory location. So this is a variable right here. We're setting our parameter coming into our variable. So this is one of our parameters, essentially. And then we are moving 42 into the other parameter. So that's that, okay. And then we are moving our parameter into EAX. We're adding, okay, so it's literally just saying add 42 to whatever our parameter is, and then return. And EAX has the final result in it, which is 42 plus whatever was coming in EDI. So this is just a simple program to add 42 to whatever parameters coming in through EDI, and then returning it through EAX. Oh, I forgot to talk about directives. Well, I'm sure you guys have had a bit of experience with directives now that I've showed off all of these programs. Directives basically are special, I shouldn't have said special instructions. Basically, they do not actually, they don't go directly into the machine code themselves. The assembler converts directives into raw binary, essentially. And unfortunately, it's almost impossible for me to show that off without going in and looking at some of the... I unfortunately don't have the ability to compile raw assembly right now. I made an attempt and it went terribly. So what we're going to do instead is just look at some of the code that I have just sitting around here for the operating system. In particular, I was planning on using this gdt.s file, but I kind of realized afterwards that this doesn't have the directives we want. We are doing global and extern directives here, but I want a string directive somewhere that I don't seem to have, which is very unfortunate. But I can show off, if we actually go in here, let's declare a string as a char pointer. We'll call it s equals hello. Okay. So this probably looks very familiar. We have this .lc0 label here generated by the compiler for this string right here, which is hello. Now what's actually going on when we compile this down is we get lc0 is basically a pointer to the first value in the string. So this quite literally is s. The pointer to lc0 is s in this program. And that's what you see we're moving. That's why you see when we do this, we're setting s equal to this constant, but this constant can't just exist. Like in C, we're just like, yes, it's the string hello. We're just setting this thing to it. But this hello needs to exist somewhere in memory. And the location that exists in memory is this unwritable section here in LC0. And then we're moving the pointer into S, and then S is storing the pointer to this constant string in memory, right? So if we actually take a look at what's going on inside of it, and this is not going to go very well if I click Intel, not ASM syntax. If I compile this to binary, we're actually going to see that directive basically completely disappear. And the reason we're going to see that directive completely disappear is because now we are in no man's land. And and if we take a look at where that string actually went, I would like to know where that string actually went. It went to this location right here. And this location right here, I don't believe shows up in our program anymore. It is at location 40204. And I don't see that anywhere. I wonder if I really wish I had GDB access to this, because I would very easily be able to actually go to that location and we would see the string stored in the memory location. Unfortunately, we do not have access to that, so I cannot show that. But just know that the directive gets converted into actual the actual characters in memory in ones and zeros, and then we are loading the pointer of that in. That's what that directive says. And there's a lot of different directives. But the one thing that you shouldn't be confused about is the fact that a .lc0 is not a directive. It's only a directive if it doesn't have the colon afterwards. Anything with a colon after it is a label. So do not confuse local labels with directives. Directives have a dot and then will normally take a parameter. Sometimes they don't. But there's a lot of very useful directives, because you can also send your directives to the assembler, like in my case with the operating system, where I'm using the global and extern directive to say, hey, I want GDT load to publicly be available to other files that need to link with this. So I can call GDT load from a C program, which we actually see me doing right here. I'm actually calling GDT load from C as if this was a C function, when in reality, no, it's an assembly function that I've just made the label to global so the linker can see it and connect these together and basically glue this call right here to this assembly method right here. And as you can see, we're actually calling return here, but we know that we're going to be calling it. The compiled C code is going to basically be running call right here. And we can just treat this as if it's a function, essentially, even though it's not. It's a memory location with a label. And in reality, I mean, that's what everything is. Functions are just an abstraction for labels with jumps. All right, so let's get back into the final thing. So we went over that. I think I've covered directives adequately enough. You can also use .long to store like literal 64-bit numbers in memory as well. You see that happen quite often when working with doubles. They'll store the double as a .long, which is kind of stupid. I would just store it as a quad. But for some reason, this is just like a carryover from the old days. And when you store a double, and honestly, that might be why they call it a double, is because it's a double precision, essentially. So you're doing 2 single precisions here and storing it as a .long followed by a .long. And in memory, this is contiguous, right, at LC1, which is just the memory location, right? So that's all for directives. I mean, there's hundreds of directives, and all the assemblers have their own directives and everything. Directives are not considered normally a part of the assembly language, and different assemblers have different sets of directives that you can legally use. NASM has a completely different set of directives, despite the fact that it's all x86. the assembler gets to determine what directives it wants. It's kind of like how GCC has all of its like secret attributes that you're allowed to use, but aren't supported on other compilers. Anyway, I don't know why I was planning on covering the stack last, but we already covered the stack. So I actually think that's everything that we wanted to go over tonight. So before we end, does anyone have any questions about the x86 language or any of the stuff that we went over tonight? I know it wasn't it wasn't a great presentation, but it was more of just walking through code together. I thought it was overall pretty solid. Any questions before we wrap up? Otherwise, we're gonna call it, I think. All right, if no one has any questions in that case, thank you for coming, everyone. Tomorrow we'll actually be going over starting your own operating system, and I hope I could make that one a lot more hands-on. I know this is very boring because no one can actually do anything, right? Like, this is just listening to me talk for like 2 hours, right? So tomorrow, I was actually planning on having a section of this where we write our own assembly programs, but I think we're just gonna ignore that and not do that unless all of you are dying to write your own assembly programs. But I mean, we've already lost 2 people, so I mean, I'd say overall we're pretty good. I'm also gonna link the site that I use. Oh, I also wanted to show this off. This is a. Does anyone want to see some forbidden C programs before we end? This was going to be the highlight of the night. Was going to be this guy right here. So there's actually a thing in the C programming language called inline assembly, which lets you call assembly code inline. Inline being in your C code, you can write assembly instructions and run some black magic using your C variables to run instructions. So the program that I've written here actually prints out everything on the stack. So let me add a new compiler here and X out of the original compiler and take a look at this guy. Because this guy right here, if we actually take a look at what he's doing, is very interesting. So this guy right here, what we're doing is I'm actually getting the RBP and RSP immediately after the stack frame is set up. I'm calling this inline assembly right here to actually. Oh, I'm in Intel mode. Let's get Intel mode. And you can see which statements are inline assembly because they're indented really weird compared to the other statements that have really nice default indentation. The ones that I'm injecting are essentially coming in with this weird single space indentation because that's literally the syntax that I'm using. So what I'm saying here is I'm going to move the value of RBP into %0 in this case is actually just referring to the parameter I'm passing in over here, which is the index of RBP. So I'm actually saying, and as you can see, these are -16 and -24 here, so we actually have quite a bit of space to move everything in because these are going to be these are pointers. So these are going to be 64 bits or 8 bytes. And we're basically moving 0 initially into them. And then in these inline assembly injections here, what we're actually doing is moving the value of RBP into them in this really convoluted way. I'm going into RAX first. RAX basically serving as a temporary. But in the end, RBP is ending up in -16 RBP X. So we're storing RBP, basically the value of it, in a memory location pointed to by RBP, which of course is very funny. And then we're doing the same thing with the RSP. And then basically we're calculating the difference between RBP and RSP to figure out the size of our stack frame. Like how many local variables do we have? And in our case, the result is 32. And I'm printing that out right here. RBP minus RSP. And despite the fact that these are pointers, I can just legally subtract the pointers from each other to figure out the size. I can print out the size. And then what I'm doing right here with this syntax is I'm actually going through the base pointer and printing out everything in our stack. So I can actually print out everything in the C program stack frame using inline assembly, this hack right here. So let's say I'm going to just add some more ints to this for fun. If I add int a equals, let's say 10, let's say int b equals 10, or let's say something more fun, 20. And now if I actually take a look and compile to binary, not compile to binary, run the compiled output, can I get the output? We actually see going on here, I'm printing out the entire stack on here. And as we can see, if I do, let's see, where's my 10? So when I actually declare my 10 here, what we're doing is we're moving 10 into -8. And if we actually see what's at -8, we see 0A. And it would actually be more helpful since I'm printing out in hex if I do 010 and 0x20. And now we're going to see the actual values in here. So at -8, you can see that I'm storing as an int 16. Well, in this case, 0x10. And we actually see that 0x10 here at -8 in the stack. And then for our next parameter, b, we're storing it at -12 RVP. So if we look at -12 RVP, we see 20 in there. So I thought that was very cool that we can literally write a C program that prints out our entire stack frame with just a very simple understanding of assembly and what's going on behind the scenes in a compiled C program. So that was really the last thing I wanted to show off. This is like the highlight of the night, is the fact that we can write these little hacky programs like this to have like raw access into the assembly with the with inline assembly directives. And of course, this is an incredibly weird syntax that I would have to spend like half an hour going over. Like we have colons left and right here. There's 2 extra colons on the end. We need clobber registers. And if we wanted to input stuff, we need another thing in between that colon. It's really its own like black magic syntax, honestly. So we're not going to be going over fully how that works. And preferably, I'm never going to use this in my operating system either. I'm always going to prefer to write raw assembly myself and then call into it from C, rather than put the assembly in the C code, because you can run into some serious issues with this stuff if you're not careful with it. Anyway, yeah. So if no one has any other questions, I'll give everyone 10 seconds to start typing if they have questions. Otherwise, we're gonna wrap up. Thank you, Carter. I appreciate it. All right. So in that case, good work, everyone. Matthew, that is not appropriate for the professional environment that I have worked so hard to set up.
I couldn't help myself.
It's okay. That's how I feel when I look at this program. Anyway, thank you for coming, everyone. I really appreciate it. Tomorrow we'll be going over the actual. We're actually going to be doing a lot more, hands-on stuff. I'm actually going to teach it. So for those who are planning on showing up tomorrow, I'll just give a bit of a preview on what we're doing. OS Dev Wiki. Oh boy, I love OS Dev Wiki. They have something called the Bare Bones tutorial. And the Bare Bones tutorial basically teaches you from scratch how to set up a Hello World operating system. And a Hello World operating system, all it does is print out Hello World the second you boot the operating system up. Now, I thought that this was a great accomplishment, and I thought that once I had accomplished this, I would be ready to get keyboard input. No, I was completely wrong. It's been I've spent 20 hours since I got this running trying to get keyboard input, and I'm still working on it. So this is a very good way to just get your basic operating system set up. So I'm going to be going over first. I'm going to go over how to build a cross compiler and why we need a cross compiler. And then I'm going to go over all of these programs all of this glue code that they have, basically. And then we're going to finish off with the kernel and printing out, finally, Hello Kernel World and compiling everything. So look forward to that tomorrow if you're planning on showing up. Hopefully it's going to be a lot more fun and you'll actually be able to run your own operating system yourself. And yes, look forward to that. I think it's very fun anyway. Anyway, thank you for coming, everyone. Have a great night. Bye-bye.